Hello. In this video, we will continue our study of applications of integration, specifically in the area of physics. We are going to investigate the relationship between force and energy, or force and work. And we're going to introduce those terms and how to interpret them. And then we're going to use a specific example of a force function known as Hooke's law that describes the force required to stretch or compress a coiled spring. Just to have a simpler example to start with, let's say I have a box sitting on the ground, and I know that the box has a mass of 5 kilograms, and I'm going to lift that box up to a height of 2 meters. What does it take to do that? What force am I working against, and how much energy am I going to expend in doing so? Well, we know that the gravitational pull of the Earth causes objects to accelerate at a constant rate, and that's what this g value of 9.8 meters per second squared is. That 9.8 value is measured experimentally. It's not exactly that. I'm rounding off a little bit. And the units of meters per second squared comes from acceleration being the rate of change of velocity. This means if I drop an object and the Earth pulls it downwards, it will increase its speed downwards by 9.8 meters per second every second. Now, one of Newton's laws of motion says that force is mass times acceleration, F equals ma. That's sort of the famous one. And so in our example, this is saying that the force I'm working against is constant because the mass of the box is a constant of 5 kilograms. That's where that 5 there is coming from. And then the gravitational acceleration is constant. That's what that g there represents. And so I'm even rounding off there to say that, g is approximately 10. That's not exact, but it's going to give us a nice round number to work with and have something to think of. So let's just say that the force I'm working against is a constant of 50. And by the way, the units on a force are measured in newtons, or kilograms times meters per second squared. You can even see where that's coming from. The acceleration due to gravity is meters per second squared, and I'm multiplying by m, a mass, which is in kilograms. So that's what the kilogram meter per second squared is coming from, and we just call those newtons in honor of Isaac Newton. Now, when a force is constant like this, then it turns out the energy required to work against that force is just the product F times d, or force times distance. So in my specific toy example here, if I'm going to lift that 5 kilogram box against the force of gravity up to a height of 2 meters, that's the distance that I'm working with, the height of 2 meters. And so that product is 100. And by the way, those units are in joules, or kilogram meters squared per second squared. That's the measurement on energy. Now in physics, we call this work. This amount of energy required to work against a force is called work. And one way, perhaps a silly way, but it might work for you, one way to remember all of this stuff that I have on the slide here, the relationship between these things, is that work makes us mad. The work required to do something is the force I'm working against, assuming it's constant, by the way. The force I'm working against times the distance. Newton's law tells me that force is mass times acceleration, so I can see right here that work makes us mad. Now, I just said it was important to know that all of that's assuming that the force is constant. What if it's not? What if the force is changing? So what if the force I'm working against follows a graph more like what I've drawn up here in the top right, where perhaps as I move further along my track, it's harder for me to keep pushing. I have a larger force that I'm working against. Well, how do I deal with that? So let's use f of x to mean the force that I'm working against, f for force, not just for function. And the input x is where I am along my track, the x input variable. What I'd like to do is come up with a way to conceptualize how much energy, how much work it takes to act against this force that is changing, that is varying, that is not constant. Well, all of that information on the previous slide, work making us mad, tells us what to do when a force is constant. Just multiply force times distance. And if the force is not constant, if it's like this graph that I have up here where it's changing with x, well, what I can do is sort of zoom in on small moments of time, very small intervals along the x-axis, along the location axis, and pretend that just for that moment, the force I'm working against is constant. So in that diagram on the top right there, let's just say over that first interval of time along, or first interval of distance along the x-axis there, that although the force is increasing, I can see it changing, let's just for the sake of simplification assume that the force is constant at the height at the right endpoint, that horizontal line that I've drawn right there. And then let's pretend that in the next moment, the force is constant and it's equal to the value at the right-hand endpoint. And then kind of the same thing, and so on. And so we can kind of just pretend that momentarily the forces are constant and know that it's not a perfect explanation of how much energy I'm expending, but maybe it's going to be a close enough approximation. Now, over each of these intervals, I can say that the total energy, the work that I'm expending on each one, is the product of x along here times the height, or force. And so what I'm getting is just the area of that rectangle for each one of those intervals. And then I can add those together, and that's going to be a good estimate for what the total work or energy that I'm expending over this whole distance that I'm pushing my object. Now, if you can imagine, I did that again, but I split up my moments of time into even more fine-grained intervals and did the same approximation process, I might get an even better estimate. And I could do that again with even finer grained rectangles and get a better estimate. And this should all sound a lot like what we did way back at the beginning of the semester when we started talking about finding the area under a curve whose height is changing, who's not constant, by zooming in on small intervals on the x-axis, pretending the curve's height is constant above that interval. The sum of the areas of those rectangles, that's exactly what those Riemann sums were. In other words, we're just kind of reinventing the concept of an integral right here. We're taking a function, in this case force, whose output value is changing, and pretending that over very small intervals that height is constant to allow us to do something simple like multiply width times height to get the area of a rectangle, or multiply force times distance to get the work or energy used over a small moment of time. And then we're going to add all those together to get an approximation of the total and take a limit as the widths of those intervals get smaller and smaller. In other words, we're just reinventing straight up what an integral is. And so that's why I have this statement in the theorem box down at the bottom that says, if I'm applying a force to move an object along a straight line from x equals a to x equals b, and the force is varying, the force is not constant, and it varies according to some function, then the work is just the integral of that function over that interval from a to b. But I think it's really helpful and interesting to see that this idea is really just the Riemann sum adding up the areas of rectangles in a new disguise. This is not something new and random that I have to memorize. This is not just an arbitrary place where integration shows up. This is a common theme in calculus of taking something that we know how to do and approaching a newer, harder problem by breaking it up into a bunch of smaller instances of that other problem that we already know how to solve. In the area under a curve problem, that was, we don't know how to find the area of a weird region, but we know how to find the area of a rectangle. In this problem, we don't know how to find the work or energy required to work against a changing force, but we know how to calculate the energy or work required to work against a constant force. And all of that's to say that we come up with this simple integral idea down here. So by the way, here's an example of a force that is not constant, which is unlike the original example I posed where the acceleration due to gravity on the Earth is constant. So when would a force not be constant? Well, here's an example. Imagine a coiled spring that naturally sits at an equilibrium position. If you have a spring and I just kind of put it on the table and I don't touch it, it's not going to move around. It's going to sit in a natural position where it's not squished, it's not compressed, and it's not stretched out. This is what I mean by equilibrium. It's just kind of sitting there without really moving. Then to stretch or compress the spring, we would have to apply a force. Let's use x to mean the distance that the spring has been moved. I'm going to use positive to mean stretched and negative to mean compressed or squished inwards. Now the force required is a function of that distance. So we're going to use f of x to mean the force required to hold the spring stretched or compressed a distance of x, depending on whether that's positive or negative. Now, this scientist from the 17th century, Robert Hooke, he discovered through some experiments and measurements in the late 1600s that that force function is actually directly proportional to the distance. It's a direct multiple of the distance. In other words, the force increases linearly as I stretch the spring further and further. And that's what it says in the theorem box down here. Hooke's law says for a spring, the force required to hold the spring at a certain distance away from equilibrium is a direct multiple of that distance. And in this case, k is a constant that depends on the spring itself, the metal material that it's made out of, how tightly it was wound when it was manufactured. It's just a constant for any particular spring. Now you might want to pause and visit this YouTube URL I've linked right here. This is this is a physics teacher describing Hooke's law and showing you how to use a force measurement device to ascertain the k value of a particular spring. And this diagram that I have down here is just shamelessly taken straight from Wikipedia, but the idea here is to show you that to stretch the spring a certain distance, that's what the x represents there, it takes a certain amount of force. This little metal disc hanging on the end of it has a certain mass, so it's going to pull the spring down. And then if I want to get the spring pulled twice as far, I need to hang 2 of those weights from the end to make it pull down twice as much. I don't have to hang 1.5 of them or 3 of them. I have to hang exactly 2 of those masses to make it stretch exactly twice as far as it would with just 1 of them. Now here's an example of the type of problem that we might deal with in our class. Let's say I have a spring and I have a force measurement device that allows me to stretch the spring a certain amount. It'll tell me how much force I'm applying to hold it at that stretched position, and I can use a ruler to measure how much it has been stretched, and I can use all that to come up with the k constant for the spring. So look at my little cartoony drawings at the top there. I have a coiled spring that would naturally rest at an equilibrium position, and if I pull it 10 centimeters outwards from that equilibrium position and hold it there, I must be applying a certain force to keep it right there. And I can set up a little device that tells me how big that force actually is. And let's say my device tells me I'm applying a force of 10 newtons to keep the spring held stretched 10 centimeters away from its equilibrium. Well, Hooke's law says that that force is directly proportional to some multiple of the stretching or compressing distance. And in my example, I'm going to say, well, 10 has to be equal to k times 10. And let me be careful about that because those are different 10s, so to speak. The 10 on the left is the 10 newtons, the force that I'm applying to hold the spring stretched that amount. Whereas the 10 on the right is the 10 centimeters of distance that I've stretched, the x. And then let me even be more careful and say that you might have caught a little small purposeful error there, which is that 10 centimeters is really not what I want to plug in for x here. I really want to plug in 0.1 or 0.10 because the standard scientific units are meters, and so 10 centimeters is 0.1 meters. So really what I have here is 10 newtons is equal to k times 0.1 meters. And so I can divide both sides by 0.1 to say k is 10 over 0.1, which is 100. That's the value of the spring constant for this spring. So let's use the same careful thinking to approach the next question, which says, what force is required to hold the spring in a position that's stretched a quarter meter away from its equilibrium? Well, a quarter of a meter is 0.25 meters, or 25 centimeters, but I'm going to use that 0.25 number to say that the force required is what I get by plugging in 0.25 for x. And 100 times 0.25, that's 25. That's in newtons. That's the force required for me to hold the spring stretched that amount. Now, it's a slightly different question to say, how much work is required? How much energy do I expend in actually pulling the spring all the way from its natural resting equilibrium state? How much energy do I expend pulling it from that state out to the 1/4 meter stretched position? The 25 newtons tells me how much force I have to apply to hold it there. But what I want to answer in the third question is, how much energy does it take to actually pull it all the way out to reach that point? Here's where I have to finally apply some calculus, which is the work is the integral of the force function. So here's me writing the force function, 100x. And the limits of integration here are from 0, from equilibrium, out to 0.25, that 1/4 of a meter away. And there I've highlighted where those values are coming from. The 0.25 is that position, the 1/4 meter from the previous question. And the 0, the equilibrium, is it hasn't been stretched at all. So the antiderivative of 100x is 50x squared. I have to plug in 0 at the bottom and 0.25 at the top. So I get 50 times 0.25 squared. And by the way, when I plug in 0 as the lower limit, I'm going to get 50 times 0 squared, or nothing, so I just didn't even bother to write that term. And crunching these numbers, I get 3.125. Remember, the units on that are joules, or kilogram meters squared per second squared. This is a measure of the work or energy required to actually pull the spring from equilibrium out to that point. Now let's say I'm at that stretched point, and I want to know how much work or energy is going to take to stretch it another 10 centimeters past that point. So just to lay out what we know so far, from the equilibrium position to stretch it out a quarter of a meter, or 0.25 meters, that's what the red highlighted part is there, that takes energy amounting to 3.125 joules. That's the work required to stretch it across to the end of that red region. Contrast that with the force required to hold it there. Once I get to that point, the force that I'm applying to keep it in that position, that's what the 25 newtons, that other answer we came up with, that's what that is. What I'm really asking in this question on this slide is how much work, how much energy is going to take to stretch it another 10 centimeters past that. That's what the green area represents here. If I've already stretched it that quarter of a meter, I'm going to stretch it a little bit farther, another 10 centimeters, or another tenth of a meter, 0.1 meters. How much work, energy is it going to take to do that? Well, I'm going to set up another integral. The function inside is force, or 100x, we got from Hooke's law. And in this case, the limits of integration are from 0.25 to 0.35. The 0.25 represents the quarter of a meter it's already been stretched, and the 0.35 represents the extra tenth of a meter that I'm going past that. Now I get the same antiderivative, that 50x squared, as I did before. I'm going to plug in my limits of 0.25 and 0.35. And crunching some numbers in a calculator on the side, what I came up with for a total after all that is 3 joules. Now notice that that's only a little bit smaller than the 3.125 joules that we came up with for the previous question. And that may surprise you at first to say, well, it took me a little bit more than 3 joules to stretch a quarter of a meter, but then it took me 3 joules exactly to stretch only 1/10 of a meter. How is that possible? Well, the whole point is that in that extra 1/10 of a meter that I stretch at the end, the spring has already been stretched out quite a bit, so it takes a lot more energy or work to pull it even farther. If you have a spring at home, or if you've done this before, try to imagine this. Once you've already stretched a spring quite a bit, it takes even more work to continue stretching it. It doesn't take the same constant force to keep pulling it apart. It's harder to do the more it has already been stretched. And so that's why it shouldn't be too much of a shock that this number is just barely smaller than this number, even though the net distances we're talking about, 1/10 of a meter versus 1/4 of a meter, are quite different from one another. All right, one final question, because I just wanted to show you how to interpret and conceptualize dealing with compressing the spring as opposed to stretching it. So let's say I have the same setup, the same spring, the same force function from Hooke's law, and I ask, well, how much work, how much energy is it going to take to compress the spring from equilibrium inwards 20 centimeters? So in other words, if I've got my spring sitting naturally at its equilibrium state, I'm going to compress it inwards 0.2 meters. And that's going to leave me this much more tightly coiled spring. Hopefully you can get that out of my terrible cartoony drawings. But the question is, how much energy, how much work does it take to do that? Well, as usual, I'm going to set up an integral of the force function, 100x. And in this case, the starting value is x equals 0 from the equilibrium. And the upper limit, the ending value, is negative 0.2 because I'm compressing it inwards by 0.2 meters or 20 centimeters. And that may look a little odd right now to see an upper limit of integration that's to the left, more negative than the lower limit, but that's not anything to worry about. Let's just plug in the numbers and see what we get. In this case, I have the same old antiderivative I keep using, the 50x squared. I'm going to plug in negative 0.2 as the upper limit, and I'm going to plug in 0 as the lower limit. And so this term ends up disappearing. That's 0. And what I'm left with is 50 times negative 0.2, and that whole thing is squared, so I actually end up with a positive value. This is saying it's still going to take some energy. It's not like I'm gaining work or gaining energy in any way. I'm actually expending 2 joules of energy to compress the spring. And I'll just point out, to conclude here, that this is the same result you would get if I asked how much work is required to stretch the spring 20 centimeters outwards from its equilibrium position. It doesn't matter whether I'm pressing inwards or stretching outwards, it's going to take 2 joules of energy to do that.